I'd like to teach you about the conservation of momentum. And just as we did in our studies of work and energy, I'd like for you to start by defining your system. Momentum is conserved within an isolated and defined system. And in this situation, we see that the net force, or the sum of forces, equals 0 in a system in which momentum is conserved. Take a look at this PhET simulation you see on your screen, in which a magenta colored ball collides with a light blue colored ball. Please notice that the arrows on each object represent velocity and momentum, where the green arrow is the velocity and the blue arrow is the momentum. Also notice that above each object, after they collide, you'll see another blue arrow representative of the overall change in momentum. Now, just because the momentum for a defined system is conserved does not mean momenta for individual objects within that system are conserved. So we need to be very careful in this unit when we analyze the momentum. We need to consider whether we're looking at the momentum of a defined system or if we're looking at the individual momenta of objects within our system. We're going to be using this equation again, which I derived in a previous video. This is the equation for the impulse. Now, when we're analyzing these situations to determine if momentum is conserved, we need to look at the sum of the initial momenta and compare that to the sum of the final momenta. Now, within a defined and isolated system, these values for both initial and final momenta will be the same. Let's go ahead and do a calculation for this particular situation you see on your screen now. Let's sum the momenta initially. So we're going to take the mass of both objects and multiply each respective object by their velocity, acknowledging that momentum is a vector quantity. Thus, we need to pay special attention to signage in our summation. As we go through and put in the values from the simulation and calculate the overall momenta initially, they sum to 0 Newton seconds. Now, also please recall that another acceptable unit for impulse and momentum would be kilograms multiplied by meters per second. So we have 0 Newton seconds initially for this defined system, which means if momentum is conserved, which it is, the final momenta should also sum to 0. So here you see a screenshot of the final momenta after the objects have collided and reversed direction. And if you were to plug in the values now, paying attention to your signage and solve, you would see that the sum of the final momenta also equals 0 Newton seconds. Let's analyze the individual momenta for the two objects in our system. Let's start by finding the initial momentum for the light blue colored ball. We can calculate it to be positive 0.5 Newton seconds. Let's look after the collision now and calculate the final momentum for the light blue colored ball to be negative 0.5 Newton seconds. Let me provide a bit of intuition here for what has occurred. The light blue colored ball had its initial momentum to the right. It struck the magenta colored ball, for an instant stopped, and regained all of its momentum, but in the opposite direction. So of course, momentum was not conserved for this object. and we can find its overall change in momentum to be equal to -1 Newton second. In fact, we can do the same for the magenta colored ball and find its overall change in momentum to be a +1 Newton second. So the change in one object's momentum is equal in magnitude but opposite in direction to the other object in our isolated system. Now, take a look at this particular scenario in which we have these same two objects within our system. Let's sum our initial momenta for this two-object system. Notice in this case here that the magenta ball is 2 times the mass of the light blue ball. In other words, it is 1 kilogram compared to the light blue ball, which is half a kilogram. Notice again, they are heading toward one another. The light blue has a velocity to the right. The magenta has a velocity equal in magnitude, but to the left. So when we sum these initial momenta, we get -0.5 Newton seconds. Let's go ahead and look at our sum of the final momenta. Notice for the light blue ball, its velocity has gone from a +1 meter per second to a -1.67 meters per second. So what happened during this collision? The light blue ball went from 1 meter per second in the right direction, stopped for an instant, upon the collision, reversed direction, and regained a magnitude of 1.67 meters per second. However, now in the opposite direction. And of course, again, we've defined to the left negative for our coordinate system. Let's look at the magenta ball, which was originally moving to the left at 1 meter per second. However, now, after the collision, it's moving to the right at about 1/3 of a meter per second. That's what happened after the collision with the magenta ball. So if we look at the sum of the initial momenta, which was -0.5 Newton seconds, and we understand that momentum is conserved within this isolated system, then the sum of the final momenta equals -0.5 Newton seconds as well. In other words, they are the same because momentum for the system is conserved. However, for the individual objects, they are not. Now, let's go ahead and look at Newton's third law, force pairs. As I mentioned in the second unit of this course, this third law is applicable to every unit within this course. So let's go ahead and consider Newton's third law within the context of the conservation of momentum. So we know that the force exerted by the light blue ball onto the magenta ball is equal in magnitude, opposite in direction, to the force exerted by the magenta ball onto the light blue ball. If we take this a step further and look at the fact that the sum of the forces, or the net force, is equal to the product of mass and acceleration, and we look at the fact that acceleration is a change in velocity over a duration of time, so v final minus v initial, we can actually mathematically consider this scenario within that context, because we know both the initial and final velocities for both balls. We know that the forces exerted by one ball onto the other are equal in magnitude, as they are mutual pairs in this third law relationship. Lastly, we know that the duration of time those two objects are in contact during the collision is the same. A fraction of a second here and a fraction of a second here. They are the exact same. So we can rearrange Newton's second law and divide both sides by the mass to isolate the acceleration, which again is nothing more than the change in velocity over the change in time. This will allow us to mathematically compare mass and acceleration within this particular scenario. And indeed, we see that the acceleration for an object is inversely proportional to its mass. Let's look at it graphically. If we looked at it graphically, we would see this relationship occurring. We could linearize this by taking it, and for the x-axis, taking the mass, and instead of graphing mass, graph 1 divided by the mass, which is the inverse of mass. That would linearize this graph, giving us a constant positive slope. In this final scenario, in which the light blue ball has 0 momentum initially, if we were to sum the momenta initially, we would get negative 0.5 Newton seconds. Again, look at the velocity of the light blue ball. It is not moving and therefore has no initial momentum. Let us now sum the momenta final. So after the collision, we see the light blue ball is now moving off to the left, and it has a velocity in the left direction of 0.67 meters per second. Let's look at the magenta ball. It was initially moving to the left at 0.5 meter per second. However, now it's moving to the left, but look at the magnitude of its velocity. It is greatly diminished from 0.5 meter per second to the left to now 0.17 meters per second to the left. Also notice that our change in momentum initially is equal to our change in momentum in final scenario. These are identical, and therefore, as is the purpose of this video, we see that momentum is conserved within this two-object system. Let's calculate the impulse exerted onto ball 2. Let's go ahead and plug in the values for the magenta ball to find its change in momentum, which would be the impulse exerted upon the magenta ball only. Again, we're only looking at this object. So its final momentum minus its initial momentum gives us an impulse of positive 0.33 Newton seconds. That would be 0.33 Newton seconds to the right. If you were to calculate the impulse exerted onto ball 1, you would find it to be 0.33 Newton seconds to the left, which again exemplifies the fact that the change in momentum for one object is equal in magnitude to the change in momentum for the other object, which leads to momentum being conserved within the system. So in this video, I've taught you now about the conservation of momentum and the fact that momentum is conserved within an isolated and defined system. However, that does not mean that the individual momenta for the objects within the system is conserved. And I'll see you guys in class.